Okay, well done. It's good that most of you are able to submit on time. That is interesting.
Sir, is
Excuse me,
partial.
sir.
Sorry?
Excuse me, sir.
Is
Sir,
partial
I
mark
submitted at sir I submitted at 8:59, but I also turned it in, and now it's showing not turned in. Well, the service has been changed. The closing time was 8:59 before, and now it is 9:03.
So today's we'll talk on fluidization. Mm, Yeah, students are able to see my screen.
Sir, hello, sir.
Yes, sir.
Yes, please.
Yes, the screen is visible.
Yeah. So this is the course distribution which we showed in the introductory class. So I have basically covered this part of the section. So far, storage of solids and transport of solids, that is pneumatic transport and slurry transport. And the pneumatic transport, we have talked about dilute and dense phase. Slurry transport requires more details of multi-phase flow, and which is also similar to the pneumatic conveying, but slightly different. So that's why I didn't go into details, but that give you an idea what is the basic idea of slurry transport. Today I want to talk about fluidization, which is also I have talked a little bit in the pneumatic transport, little more details about fluidization I will explain now. In the next class onwards, I will start talking about these ones. And so this is the fine particle characterization. We will also look into this little later. Fine particle characterization. And so today, in today's class, I wanted to talk about fluidization. I want to talk about fluidization, which is since it is related to the pneumatic transport, that's why I wanted to cover this topic today so that you'll all be able to relate more easily. Then we will see solid liquid separation and the fine particle characterization. All right. So that's the place where we are standing. I have talked about these parts already: storage, transport, and dynamics of particles in gas medium. Now I'll see. Today we are going to discuss about fluidization. So I already mentioned what is fluidization, what is the difference between pneumatic transport and fluidization. I have already explained, but let me revise or recapitulate that part again. So let's say there is a cylindrical pipe where we have a support, a porous support plate. This is a porous support plate on which these particles are resting. So when the particles are stationary, this is called packed bed. When the particles are stationary, it's like a bed of particles are lying on a stationary plate, and such type of bed is called packed bed. Then when we introduce a gas with certain flow rate, when we introduce a gas with certain flow rate, it could be gas or liquid. When we introduce a fluid, with a certain very low flow rate, what will happen? The fluid will just flow through the void spaces. The fluid will just flow through the void spaces. So we have gravitational force act in the downwards, gravity acts in the downwards, and the frictional forces or the drag forces offered by the fluid on the particle. The drag force is also termed as frictional forces or pressure forces, which acts on the upward direction. Also, buoyancy force also acts in the upward direction. Buoyancy force. Buoyancy force acts on the upward direction. Because the particle has to replace by the fluid, if at all it has to lift. So buoyancy force acts in the upward direction. When the velocity of the fluid is very low, the drag force and buoyancy force will be lower. The drag force will be lower. Buoyancy and gravity always will be remain same, but where a drag force is a function of velocity. The drag force is a function of velocity. So when the velocity of the fluid is very low, the drag force is lower, and the buoyancy force, when the sum of the drag force and buoyancy force is lower than the gravity force, the particles will be remain stationary. When the gravitational force is overcomes the drag force and buoyancy force, the particles remain stationary. So since the velocity of the fluid is very low, since the drag force is low, the fluid has to move through the void spaces present between the particles. So in this state, although the fluid is moving, but the particles remain stationary. The particles remain stationary, and such condition is called again Battered bed. Such condition is again called as Battered bed. Maybe I'll just keep this buoyancy force. So I will just write buoyancy B. Okay. When I increase the flow rate slightly, what will happen when these two balances? When the gravitational force balances the drag force and buoyancy force, when the gravitational force balances the drag force and buoyancy force, what will happen? The particles tend to just about to rise. The particles tend to about to rise. At that state, the particles will move wherever they are, but there will be slight increase in the bed height. There will be slight increase in the bed height because the particles are just moving. That state is called minimum fluidization. So the void fraction and all the bed height will be same as Battered bed, because the fluidized means the particles are about to move, upward direction, just about to move. That state is called minimum fluidization. So at this minimum fluidization, the bed height of the Battered bed, the bed height of the minimum fluidization will be same. There will be very slight increase, so hence we can assume it to be same. The void fraction of the minimum fluidization condition will be same as Battered bed condition. The bed height of the minimum fluidization is same as the Battered bed condition. So whatever conditions are there in the Battered bed condition will be same in the minimum fluidization condition, but the particles are about to rise. If I increase the velocity slightly higher than minimum fluidization velocity, what will happen? That's why I just kept it here, increasing the gas flow rate, increasing the fluid flow rate. So if I increase the velocity higher than minimum fluidization, the particles will move upward and they will mix thoroughly along with the fluid. The particles move upwards and mix along with the fluid. Here, the particles tend to behave like a fluid, hence this is called fluidization. What is the advantage? The particles mixes continuously, and that is what because of this continuous moving, the continuous movement of the particles in the bed, it makes concentration uniform, it makes efficient heat transfer, because whenever we have a continuous mixing, uniform mixing, we will have a good heat transfer. So whenever you wanted uniform concentration profile, whenever you wanted to have good heat transfer rates, we prefer fluidization condition. So fluidization is useful whenever we have a heterogeneous catalytic reactions. Heterogeneous catalytic reactions means we have a catalyst, we have a solid catalyst, and reactants and products are fluids. And the reactants and products of fluids, then we prefer the fluidization conditions for the efficient conversion of the reactants, efficient heat transfer if it is an adiabatic if it is an exothermic reaction, efficient uniform concentration profile for the uniform reaction rates. So the fluidization has many advantages because of this continuous mixing of the particles. But one important thing in fluidization, the height of the bed, the height in which the particles are lifted remains limited to certain height, If I increase the velocity higher than terminal velocity, the relative velocity is higher than terminal velocity, then we have the pneumatic transport. I have explained this earlier, but I am again explaining to distinguish between what is packed bed, what is minimum fluidization, and what is the fluidization state. We already talked about pneumatic transport, but in this class we talk about this one. With the particles stationary, when the fluid is moving, that's called packed bed. And the particles are about to move, about to rise up, and that state is called minimum fluidization. Whatever conditions maintained in the packed bed, the same conditions are applicable to the minimum fluidization because the particles are just stationary. And if the velocity of the fluid is higher than minimum fluidization velocity, then fluidization will happen. And in the fluidization, the particles will be moving upward, but limited to certain height, right? So this is packed bed and increase in the gas flow rate. And here we have again packed bed. This is same whatever we just saw. And suppose if I measure the pressure drop across this fluidized bed, if you want to measure the pressure drop across this fluidized bed, and I hope you know that we can use U-tube manometer to measure the pressure drop. We can use U-tube manometer to measure the pressure drop. I think all of you know this one. This is the U-tube manometer. So this is the U-tube manometer which is connected between the inlet starting of the bed and between the last point of the bed. So if you measure the pressure drop, how that pressure profile looks like. So I have taken the packed bed condition here. There is no gas flow rate, which is A. And there is some gas flow rate, a fluid flow rate, that is B. And the velocity of the fluid is such that the bed is in minimum fluidization conditions. That condition is C. And if the fluidization takes place, that condition is D. And those things are marked in the pressure drop versus velocity. So here we measure the pressure drop across the bed, and pressure drop across the bed, and this is the pressure drop across the bed. So you can see at zero velocity, zero pressure drop. There is no fluid flow and there is no pressure drop. When I increase the velocity up to a certain point, the pressure drop across the bed increases because the pressure drop is proportional to velocity. And I'm sure all of you know delta P equal to FLV square by 2D. Here V is velocity. Velocity increases, pressure drop increases. So delta P is proportional to V square. So as when the velocity of the fluid increases, when it comes to the B condition, hence the pressure drop increased. And when it comes to C condition, this is the C condition, the pressure drop increased from B to C because the velocity is increased. But once it attained, see this is C condition, the C condition where we mark as minimum fluidization. This is UMF, the velocity at which the minimum fluidization is taking place. That is the fluid are about to rise. That is called the minimum fluidization. Here I have marked as a minimum fluidization. After minimum fluidization, once it attains fluidization, the pressure drop will remain same. The pressure drop will remain same. The whatever velocity you're increasing further, that will be compensated by the fluid motion. Whatever increasing velocity beyond the minimum fluidization, that additional energy is only utilized for the particles to move. But if we go beyond, if I go beyond further the pneumatic transport, if we go beyond the pneumatic transport, again that will change, further decrease. This is up to fluidization. But once it goes to pneumatic transport, where relative velocity is greater than the terminal velocity, then the pressure drop will further reduce. So the study period is only up to the fluidization condition. The study period is only up to the fluidization condition. Why this is increasing? Because this is function of length of the bed. This is a function of the length of the pneumatic transport. That's which further decreases. So this is the pressure profile. So one important thing I want you to understand is that whatever pressure drop we attain at minimum fluidization condition will be same for the fluidization condition. Whatever pressure drop we attain for the minimum fluidization condition, that will be same for the fluidization. After attaining minimum fluidization, the pressure drop will remain same. Delta P by L, I mean. Not delta P, I think I'm mistaken the written here. Delta P by L. Students kindly note it. Delta P by L will be remain same. Delta P by L will remain same. So that is the important message from this graph. From this graph, what we can understand that the pressure drop at minimum fluidization condition will be same as the pressure drop at fluidization condition. Pressure drop by length, delta P by L. We all understood what I am trying to say here. So I have explained what is packed bed condition, what is minimum fluidization condition, what is fluidization condition. From the pressure profile, I have explained that after attaining a minimum fluidization, the pressure drop per unit length will be remain same. So there is an experimental observation, and theoretical observation is that whatever additional velocity, whatever additional kinetic energy you are supplying by increasing velocity higher than minimum fluidization velocity, that kinetic energy is used to lift the particles. Hence, the frictional forces remain same. Since the particles are behaving like a fluid, the pressure drop will remain same. So we can just see how typical fluidization works. Let's say this is the bed of particles. This is the bed of spherical particles. If I introduce a gas, what will happen? See, this is the typical fluidization. The gas, whatever fluid is coming, that helps to lift the particles, to move uniformly. Now we can see this is color coding, how the velocities are varying in the bed, how the mixing will take place in the bed. It is showing, and it has beautiful animation, and these are the trajectories. Now, if you see the real-time bed, the previous one is simulation one. This is the real-time bed, and if you zoom in, if you take an image at very high magnification, and if you go, these are the particle behavior. This further magnification, 15x magnification, and this is the further high magnification. You can see the particles are uniformly mixing. If you go very high magnification, and you can see that particles are uniformly mixing and hitting each other. So this way, the fluidization helps to continuous mixing of the particles in the column. This will make the concentration uniform, heat transfer uniform, and it has very wide applications in catalytic reactions and the mass transfer application. So, sorry, I just copied this equation from the book, so it's not so clear. But anyway, I'll upload the book chapter, and you can see the equation clearly. Pressure drop for the packed bed. This is called Agni equation. This is the famous equation, and definitely this equation will be derived and taught in the fluid mechanics course. So I am not deriving this equation. In fluid mechanics course, you will learn fluid mechanics, FM. In fluid mechanics course, they will teach you this derivation of this equation. So I'm not talking about the derivation, fluid mechanics course. So this is again equation delta by H or L equal to 150 into 1 minus epsilon. Here epsilon is void fraction. Void volume by the total volume. Void fraction. Nu is viscosity. Viscosity of the fluid which is flowing. U is velocity. U is velocity. Here X SV, surface to volume average diameter. Here SV is surface to volume. I'm sure you learned in the Manoj sir's class how to get the surface to volume average particle diameter. This is particle diameter. X is particle diameter. Particle diameter. Here SV refers to surface to volume ratio. Surface to volume ratio. Plus 1.75, 1 minus epsilon is void fraction. Epsilon cube is again void fraction cube. Rho F is fluid density. Again, U is velocity. Rho F is fluid density. Fluid density. U is velocity. Again, X SV is particle size. Particle size, not diameter. Particle size. Right? So that is about battered bed. In case of fluidization bed condition, the gravitational force balances the drag force and buoyancy forces. The gravitational force balances the drag force. As I showed earlier, the gravitational force acts from the top, buoyancy force or pressure forces acts from the bottom, and so drag force or pressure force acts from the bottom, and buoyancy force acts also from the bottom. At fluidization conditions, beyond the minimum fluidization condition, the gravitational force balances the drag force and the buoyancy force. The gravitational force balances the drag force and buoyancy force. Right? So, drag force I have taken left side. The gravitational drag force keep it left side, and buoyancy force is brought this side. Buoyancy force is brought this side. So the drag force can be estimated as pressure drop into area. Drag force and pressure forces remain same. So the drag force is estimated as pressure drop into area, and gravitational force minus buoyancy forces I brought it in the right hand side. Gravitational force equal to drag force plus buoyancy force, and drag force and pressure forces remain same. Since the drag force can be estimated as pressure drop into area. Drag force can be estimated as pressure drop into area. So the pressure drop is delta P. The pressure drop is delta P, and the area is A. And just erase this. Looks odd. Yeah. Pressure drop is delta P, and the area is A. Gravitational force is nothing but mass of solids into G. The gravitational force acting on the solids into G. Buoyancy force, I'm sure all of you know the buoyancy force. Do anyone know the definition of buoyancy force? Can anyone say buoyancy force definition? Students, anyone remember buoyancy force?
So the force that is equivalent to the amount of
So let's say this is the
fluid
fluid,
by the particle.
right? Let's say this is
According
the
to
stagnant water. Let's say this is the stagnant water. And this is the stagnant water. Let's say you have dropped a steel ball. Let's say you have dropped a steel ball. So when the steel ball moves downward direction, what it does, the steel ball replaces the fluid, right? The steel ball replaces the fluid. As the steel ball moves, the steel ball replaces the fluid. Wherever as it is moving, the steel ball replaces the fluid. Amount of force required to replace the solid particle, the amount of the force required for a particle to replace that fluid by the solid particle is basically known as buoyancy force. So, amount of force required to replace the fluid by the solid. So, basically, in a calculation point of view, buoyancy force is nothing but mass of fluid equivalent to solids. The mass of fluid equivalent to solids. Mass of the fluid which is equivalent to solids into G. The buoyancy force is nothing but the mass of fluid equivalent to solids. How do we calculate mass of fluid equivalent to solids? We know the volume of particle, and when it replaced by the fluid, there will be volume of fluid. Volume of fluid. Volume of fluid is multiplied by density of the fluid gives the mass of fluid. Volume of the fluid into density of the fluid gives the mass of the fluid. Since volume of the particle is equal to volume of the fluid, the buoyancy force can be calculated as volume of the particle into density of the fluid. Volume of the particle into density of the fluid. Volume of the particle into density of the fluid. Vp into rho f. Here in fluidized bed, we don't have only one particle. We have multiple particles. If we want to calculate mass of solids, we know the void fraction is solid volume. Void fraction is void volume by total volume. What is total volume? Void volume plus solid volume. Void volume plus total volume is nothing but void volume plus solid volume. Solid volume. 1 minus epsilon. That is, if I do 1 minus epsilon, what you will get? Solid volume by void volume plus solid volume. You will get same denominator, which is nothing but the total volume. So total volume is referred as volume of bed. So solid volume equal to 1 minus epsilon into total volume. Solid volume equal to 1 minus epsilon into total volume. So volume of bed into 1 minus epsilon gives the mass of solids. Volume of solids. If I multiply with the density of the particles, give the mass of solids into G. Similarly, if you want to calculate the buoyancy forces, the volume remains same. The volume of bed into 1 minus epsilon. Instead of rho p, instead of finding the mass of solids, we have to find the mass of fluid. So we multiply with the rho f. So this way we got delta P into A equal to volume of bed into 1 minus epsilon into rho P into G minus volume of bed into 1 minus epsilon into rho F into G. So this is the formula.
Sir, I had a doubt.
Volume of bed into 1 minus epsilon and G remains same. The volume of bed can be estimated as area of the bed into height of the bed. Since this is cylindrical or whatever cross section, the volume of the bed can be estimated as whether it is rectangular cylindrical cross section, we get area into height. Area into height is the volume of bed, and you get this expression. Okay? You get this expression. Volume of bed is
I had a doubt, sir.
1 minus epsilon into G. And I have taken, this is common, I have taken rho P minus rho F.
Hello, sir.
So basically, I think there is something here is not visible because left hand side, right hand side area is there. I just cancel the area. And I got this delta P equal to height of the bed into 1 minus epsilon is the void fraction into G into rho P minus rho F. So from the graph, again I did this mistake. Delta P by L at the minimum fluidization equal to delta P of fluidization by L. L or H. L or, and we are using height of the bed H, so we will put it as H. Again, I did the typo here. I showed earlier in the graph that the pressure drop at minimum fluidization condition by the height of the bed equal to pressure drop at fluidization by the height of the bed. So this is has been observed from the experiments. It's the same thing. I just put it here. So the pressure drop at minimum fluidization will be similar to the almost equivalent. There will be slight increase, but almost equal. That error is only 1%. Error is 1 to 2%. Error is 1 to 2%. So that's why we can approximate delta P by H. Delta P by H at minimum fluidization equal to delta P of fluidized bed by H. So this is the expression we got in the previous slide. Height 1 minus epsilon. Height is there. The height taken to left hand side because this is delta P by H. Delta P by H. So 1 minus epsilon into rho P minus rho F into G, and this is the Ergun equation I showed in the before. Here UMF is given because this is only valid at minimum fluidization condition. This is only valid at minimum fluidization condition. This is equation for the minimum fluidization condition. The right hand side Ergun equation is for the any packed bed. But since we are equating, the velocity has to be minimum fluidization velocity. Velocity has to be minimum fluidization velocity. So this expression is used to find out minimum fluidization velocity. Because we know void fraction, we know the void fraction, and we know rho P, rho F, and G, all the values. We can relate this one to calculate. We can relate this one to calculate the minimum fluidization. We can relate this one to calculate the minimum fluidization conditions. So in a normal case, if somebody say what velocity we need to operate to get the fluidization, first of all we have to use this equation, then we have to calculate the minimum fluidization velocity, and usually we operate 2 times the minimum fluidization velocity to get the good fluidization conditions. Good fluidization conditions. So what particles behave well, what particles will behave improperly is characterized by the Geldart charts. I also showed earlier in the dense phase transport, I've showed this chart. But this is very, very simple, but very, very beautiful sheet, very, very beautiful chart. It is extensively used by the many people who work with solids. This is rho P, density of particle, and rho G, density of the gas. Okay, G refers to gas. As soon as you know what fluid you are using for the fluidization and what particles using for the fluidization, without knowing anything, we know this density property, and we know the density property, and we know the particle size. So based on knowing the density difference and the particle size, whether it is type 3, type C fluid, or type A fluid, type B fluid, type D fluid can be easily found out from this Geldart chart. We can easily found out from this Geldart chart. So for example, the rho P minus rho G is 2000. The difference is 2000. And if the particle size is, let's say 0.1. The particle size is 0.1. Now we can clearly see that this falls under type B. It falls under type B. That way, just by knowing the simple properties, we can know what type of fluid it is. Now here, he has given the properties. If it comes under group C or type C, Geldart type C particles, the cohesive forces are very high. The cohesive forces are very high, hence difficult to fluidize. Group A, so this zone, group A means this zone. Whatever particles fall under this zone are very good for fluidization, ideal for fluidization. Okay. Application is cracking catalyst, catalytic cracking operation, or example of the fluid. And group C is typical floors and cements. Group B can be fluidized, but it will form the bubbling fluidization. Can be fluidized, but there will be bubbling fluidization. There will be chance of bubble formation in the fluidization. Group D is, since it's crossing 1 mm, for the group D particles, they're coarse solids. Coarse solids can be fluidized, but it requires lots of energy from the fluid. Because it requires very high velocity to fluidize. It requires very high velocity to fluidize. So if the particles crosses 1 millimeter, it is difficult to fluidize at the, it can be fluidized, but amount of energy required by the fluid or the gas velocity should be very high. That's why they don't prefer group B for the fluidization. Group A and Group B can be fluidized. Group A, Group B can be used for the fluidization condition. I showed earlier Group A and Group D can be used for the dense phase transport, and here Group A and Group B can be used for the fluidization. Group C and Group D are not recommended to use for the fluidization. Group C and Group D is not recommended to use for the fluidization. So there are different types of fluidization takes place. There are different types of fluidization takes place. Let's say this is the fluidizing bed. Simple fluidizing bed is a simple cylindrical pipe where particles are uniformly distributed. The particles are uniformly distributed. So this is uniform fluidization without any bubbles, without any obstructions, without any problems. But such kind of fluidization is very, very rare. Such kind of fluidization conditions are very, very rare. But what commonly happens is bubbling fluidization. What commonly happens is bubbling fluidization. We ideally wanted uniform fluidization, but what commonly occurs is bubbling fluidization. You can see the gas comes as bubbles and goes away. The gas comes as bubbles and goes away. And this is this here I'm showing only big bubbles, which is not usually recommended to have such big bubbles. And this another type of fluidization which happens in usually, but which is not recommended, which is not, this kind is not preferred, but this is happens. That's called slugging. Slugging means what you can see. You can see here. In case of slugging, some area will be no fluidization. There will be big gas bubble. There will be small bubble comes and agglomerate and forms a big bubble and suddenly burst. The whole bubble suddenly burst and all the particles suddenly will fall. What you will see is big bubble comes and goes up to very height, suddenly burst. The bubble will burst and particles will suddenly jump back. The big bubble forms. See, the big bubble forms and fluidization happen, but whole bubble bursts and again falls back. So here the fluidization is happening, but it's not a uniform fluidization. Fluidization is happening, but uniform. It is not a uniform fluidization. This is spouting, just like we have seen in the silos, where the fluid just takes the intermediate, the one narrow path, and fluid moves. The spouted bed is nothing but the fluid takes one small narrow path and goes upward, and the fluidization will not happen both sides, left hand side, right hand side. You can see the fluid takes only small narrow path and flows, but in this case the fluidization will not happen. In this case, these particles will not be fluidized and these particles will not be fluidized. This is called typical spouted bed, and which is seen, we have seen this condition in the silos also. If you take highly cohesive powders, we can see instead of uniform mixing, all the particles are stacked together, and you will see only small channel of gas through which the fluid moves up. Through a small channel of gap, the fluid moves upward. Or sometimes small bubbles will form, and it will form like a big bubble, and whole bubble will collapse. Again, all the particles will fall back, just like I shown this spouted. So type C powders can form spouted bed or can form the slugging. Type C powders can lead to spouted bed or can lead to the slugging condition. That's why type C is not recommended, used for the fluidization. Type D is not recommended because it requires high amount of fluid flow rates, high amount of energy for the fluidization. So type C leads to this. Type C leads to the slugging or spouting. Type C leads to the slugging or spouting. That is why it is recommended to use A and B. A and B types of powders are recommended to use for the fluidization. In case of A, we might get uniform fluidization. In case of B, we get the bubbling fluidization. So this is the typical bubbling fluidization we get for the type B solids. Type B solids, we get this type of fluidization phenomena for the type B solids, which I showed here. Type A can lead to bubble formation, but those bubbles are uniform. It will not be like a very random bubble formation like what I shown in this video. So type A, see this is more preferred types of fluidization. All the particles are uniformly mixed, but this is very, very unusual to happen. And this is the type A. Type A can lead to some bubble formation, but these bubbles are stable bubbles. It won't burst in between. It won't cause any irregular patterns, what I showed in the video. Type B can lead to that irregular bubble formation, which I showed in the previous video. So this is the uniform fluidization, and this is the bubbling fluidization, which happens with the group A particles and often. Guys, you all understood what is fluidization, what is happening in the fluidization? Do you have any questions? Students are able to understand?
Hello, sir.
Are they?
Hello, sir.
After this, Strandregum 117.
Hello, sir. I had a doubt actually.
Oh, my mic is muted, sorry. Speaker. No. I think because you're saying something, but I could not hear because I didn't keep my earphones. Yeah.
Hello, sir.
Yes, Vignesh.
Sir, I had a doubt in that equation, sir. In the pressure drop equation for fluidization. There, both sides you took 1 minus epsilon.
Yeah.
So for the fluid part, we should take epsilon, no, sir. Why 1 minus epsilon?
This one, huh?
Yes, sir. Before this, we had derived it using the drag force equation, no, sir. Drag force is
correct.
yeah, here only, sir. Last line. Volume of bed into 1 minus epsilon rho f.
Correct.
Here it should be epsilon.
No, if you put epsilon, what will come? You get the void volume, no?
Yes,
volume
sir. In that only the fluid would be there, no, sir.
But we are fluid density, fluid gravity. The fluid is flowing upward, right? The gravity acts in the downwards, right? The gravity acting on the particles only. So this is the fluidized bed, and the particles are rotating, and the fluid is moving upward. The fluid is moving upward, and the solids are downward. And so the gravitational force, fluid offers the gravitational force, the particles also offer the gravitational force. But compared to the gravitational force of the particles, the fluid gravitational force is very, very, very minimal. That's why we take the gravitational particles. So the gravitational force, see GF, is mass of particles into G, right?
Yes, sir.
Mass of particles into G. So that's what I wrote, mass of solids into G. If I put epsilon here, I will get the void volume, not the particle volume.
Not, sir. Not in the particle case. I am asking for the fluid case.
Buoyancy force, you mean to say?
So fluid case, rho f into 1 minus epsilon.
Oh, this one.
Yes, sir. Second term, subtracted one.
This is buoyancy force. Buoyancy force is nothing but mass of fluid equivalent to solids. That's why I explained here. Suppose we have a.
Okay, sir. Got it, sir. That's why we had taken 1 minus epsilon. I had a doubt in that.
Yes. Correct.
Got it, sir. Got it, sir.
Thank you. Any other questions from any other students? Hope you're able to understand what I'm trying to explain. So these are different types of fluidization. So let us solve one question and we'll end this topic here. So I will share the solution sheet for today's test later. Probably by tomorrow I will share. And then we'll evaluate all the students' quiz marks. Then I will upload it. So before we go, so we want to solve a problem. 3.6 kgs of solid particles. 3.6 kgs of solid particles having density 2590 kg per meter cube, and the particle mean size, surface to volume mean size is 748 mm. 748 mm, I think microns, not mm. Microns. 740 mm is not possible to fluidize. It's possible, but takes so huge amount. Even 1 mm I showed in the Gelrad chart, it is difficult to fluidize. So the main particles 748 microns form a packed bed. 3.6 kg of solid particles form a packed bed of height 0.47 meters. So here, this is a bed. This is the support plate, distributor plate. 3.6 kg of particles are packed, just placed. 3.6 kg of solid particles are placed in this packed bed. And once you pack these particles in a bed, it is leading to a height of 0.475 meters, and the diameter of this vessel is 0.0757 meters, and they're using water to fluidize. So water density is 1000 kg per meter cube, viscosity of water 0.01 pascal second. So they're asked to calculate what is the pressure drop at incipient fluidization and what is the superficial liquid velocity at the incipient fluidization is also known as minimum fluidization. Okay. Incipient fluidization is also known as minimum fluidization. Another name for the minimum fluidization is also called as incipient fluidization. And pressure drop across the bed at velocity of 1 meter per second, and bed height is 0.6 at 1 meter per second, and what is the void fraction. So here I just properties. Mass of solids is 3.6 kgs, density is this one, and particle size is 748 micron. Packed bed height is 0.475, diameter of the bed, water density, and viscosity. So first of all, we have to find out the void fraction. Just now we have seen solids volume equal to 1 minus epsilon, 1 minus void fraction into volume of the bed. Just now we have seen this. So I think I've used that one. So 3.6 is the solid volume, and void fraction I need to calculate. We will calculate the volume of bed. Volume of bed is 3.14 pi by 4 d square. Diameter of the bed d square into height by 4. So solids volume will be, how we'll calculate solids volume. I have to divide, this is solids volume. I have to calculate the solids volume as mass of solids by density. Solids volume. So this is the solid volume, and this is the volume of bed. 1 minus void fraction is solid volume by the total volume. Total volume. So void fraction is equal to 1 minus this one. So void fraction is 0.35. I can take as roughly 0.35. This is the void fraction. So we know this expression at the minimum fluidization. This equation is valid to find out the Ergun equation equal to pressure drop at minimum fluidization. So using this equation, so first of all we have to calculate the pressure drop at minimum fluidization, delta P minimum fluidization, and we have to calculate UMF. So we will substitute here, students, and just take 2-3 minutes. Those are the next class, they may leave. I will just take only 2-3 minutes. Those who have the next class, they may leave. And anyway, I'm recording this so that you can check later this question. So I calculate 1 minus epsilon. I'm just calculating the left hand side time. 1 minus epsilon into rho p. Rho p is particle density minus fluid density into 9.81. So this is the left hand side term. Then I'm calculating this term. This is equal to 150 into 1 minus epsilon square into viscosity. This is in SI units, Pascal seconds, 0.01. EMF we have to calculate, so we don't know that value. Divided by epsilon cube into x SV square. X is nothing but particle size. This is square. I have to convert it to meters. I'll just convert it. Divided by 1e minus 6. I'm just converting microns into meters. One E6 microns. So this is the term except UMF. Now I have to calculate term here. It is 1.75 into 1 minus epsilon into rho F, a density of the water, divided by epsilon cube. XSV is microns. I got this one. So this is UMF square, and this is UMF, and this is the constant. So basically, we got the quadratic equation: ax square plus bx plus c. Now I want to find out UMF. How do I find out UMF? Just we will find out the roots. What is root? Minus b plus or minus square root of, because we want to find the roots of the quadratic equation, minus b plus or minus square root of b square minus 4ac whole divided by 2a. Am I right? So this is the expression for finding the roots of a quadratic equation. So since this is minus c, I'm just putting minus here. I'm just putting because we need to bring this on the right hand side and make it 0. So answer will become minus c. UMF is minus b. This is b minus b plus square root of b square minus 4 into a into c. Divided by 2a. 2 into a. So too little. Gone wrong. Okay. So this is 1. Now this is one root. Then we will do the. So if I do plus, I'm getting 0.003 meter per second. If I do minus here, negative. So negative is not possible. We have two roots. One is positive root, one is negative root, and negative root is not possible because negative velocity is not possible. Hence, we have to take only positive only. Where did I gone wrong? Battered Bed. Why it is showing wrong? EMF is very little. It's not possible to get this low velocity. I'm making somewhere some mistake. So this is converted to meters anyway. 6, 3, 4, 5, 6. That's correct. Okay. I think somewhere I made mistake, and you all please cross check. So this is the minimum fluidization velocity. There is no fundamental mistake. Must be small mistake in the calculation. Minimum fluidization velocity. Now calculate pressure drop. Fluidization velocity. So we know this is the delta P by L. This is basically del P by L, right? So we'll just calculate 1 minus epsilon rho P minus rho F, rho P minus rho F, 9.81 into bed height. Bed height is 4.75, and this is the pascals. 4815 pascals will be the pressure drop at minimum fluidization. Now we know the pressure drop at minimum fluidization equal to pressure drop at fluidization. So part C also same. Pressure drop at 1 meter per second. Drop at 1 meter per second will be same, right? Because minimum fluidization pressure drop is same as fluidization pressure drop. So these two will be remain same. So these are the answers. And the bed height is 1 meter per second. The bed height at 1 meter per second is 0.6, and calculate the void fraction. Calculate the void fraction. So how do we calculate void fraction? Void fraction equal to 1 minus solid volume by total volume, bed volume. Volume of bed. I should not use equal to. So solid volume remains same because particles did not change, right? The particles did not change. Solid volume will be remain same. So here we calculate the solid volume, and now we have to calculate the volume of bed. Volume of bed is nothing but area into height. Area into height. Into height. So this will be 3.14 into diameter square by 4. So maybe I'll just put in brackets into height. Height of the bed is given as 0.6. Here height of the bed is given as 0.6. We should not take 0.475, but take 0.6. So void fraction is 1 minus solid volume divided by the bed volume. This is the void fraction. So that is the anyway, I'll save it. So that is the answer for part D. Okay, thank you, students. This is the part A, part B, and part C, and this is the answer of the part B. Fluidization. Yeah. Thank you. If you have any questions, please ask me. I think I have taken long time, more than what I said, and sorry for that. And thank you so much. If you have any questions, please let me know. Otherwise, we'll meet on 11th.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.